She says Julie.
Today? What is
Her
that?
local language. Like,
Today. Okay. Which language is that?
Julie is said every time, right? Even in the evening.
Julie has no very. You can say for thank you, hi, and then bye, and so.
Very convenient. Okay. Namaste. So today's Friday, and today is the halfway point of our course. A week from now, actually next Thursday and Friday, we will schedule your presentations. So please, over the weekend and in the beginning of next week, work on looking up information and bringing together what you want to present. Really, the goal of the presentation has two goals. One is for you to learn something independently about a topic that is of interest to you connected to tree rings. And secondly, for you to teach that to the class. Okay, so in your presentation time, that's when you can communicate with all of us what you have found out about this topic. All right? Some people in their list of topics had a very broad topic. Like one of the topics is using dendrochronology in forest management. That's very broad because there's many different kinds of applications. So as you work on that topic, it is appropriate and good to make it more specific. And you don't, it's a short presentation, so it's better to communicate 2 or 3 or 4 key points, not to try to make it a very exhaustive bibliography and read 50 papers. That's not the intention. But the intention is that if you pick a particular topic, that you can show 3 or 4 slides that make 2 or 3 points, and that's good. That helps all of us learn something from your presentation. Okay? If you have questions about your topic or about things you find or about how to present it, then feel free to ask me. We'll come back to this on Monday and Tuesday and give everyone a chance to be thinking in the same way about these presentations. Also, since it's the weekend, I put up this cartoon for us. So it's just a reminder for the weekend to enjoy other parts of life besides classrooms and work. This is done by this person here, Jorge Chang, and he is a cartoonist. He writes what's at the bottom there. It says PhDcomics.com, and it's sort of academic comics. So for people in the academic world, this can be our weird sense of humor.
very common here as well.
Ah, okay.
We keep on posting this.
All right. Would one of you mind turning down some of the lights? I think we're starting to know which switches. Oh, thank you. Thank you. That's good. Oh, this is nice. Now we have a laser pointer too. That's enough. We don't want it to be too dark. And then we fall asleep. Alright. Perfect. Okay, so today we're going to talk about assessing the accuracy of cross-dating. And we're going to talk in particular about a program called COFECHA. And we're going to discuss how it works and then actually use it with some data. COFECHA is an important program in dendrochronology. because it helps us assess the accuracy of cross-dated samples. So when you start actually working with your samples, you often use the program Cofecha. There are other programs that work in similar ways. Yesterday we looked at a couple of examples of measurement equipment and software. We looked at one called Dendro, which uses scanned images. And then we looked at an example from a company called LinTab, which has a measurement stage that physically moves the sample to measure the ring widths, but it comes with a software that works in many ways similar to what Cofecha does. So Cofecha is not the only option, but they're all kind of doing similar sorts of things. They're looking at the correlations of measured tree ring width series, measured tree ring widths, with each other or with a master chronology. So Cofecha is free, it's readily available, and it's been widely used in literature, so it's a good starting point for us to look at this kind of software. So first we're going to discuss how it works in the presentation, and then we'll use the program. We can just use it right here on this computer. If you have brought a laptop, you can download it right now also and use it yourself. And I'll show you where the tree ring data are that you can download and look at. Okay, so these are the topics. What is it? What does it do? What does it not do? Which is an important issue. How do you get it? How can you run it? And then we'll look at the output. Okay, so Cofecha is described. Cofecha is a relatively old program, probably from about the 1980s. In 2001, Henry Gracino Meyer, who we've mentioned so many times, one of the reasons we mention him a lot is that he chose in his career to write some papers like the one shown here, describing more detail about how to do things that people had already been doing, but had not formally written down what are all the rules and everything you need to know. So for example, I sent you a paper that he wrote about using the increment bore. Well, people have been using increment bores for close to 200 years, but he chose to write a paper that gave you all the information about it. And similarly, this is another reference, and I'll send this to you later in an email, but this was published in the other major journal related to tree rings, the journal called Tree Ring Research. Yesterday we looked at an example from the journal Dendroecology. And so this is a report or information about how to use Cofecha. And so you may find that useful if you end up using Cofecha. So Cofecha is an invented term. And unlike most names of many names of programs are acronyms, so they're from the initials of a longer word. This actually just means co and fecha means date in the Spanish language. So the person who put it together is Richard Holmes, wrote the original version, I think, in the Fortran language, back in the very old days of computers, before you guys were all born, when people were typing in commands or even making commands on punch cards and feeding the cards into a big machine. So way back when this program was written. So Cofecha uses, this is a quote, segmented time series correlation techniques to assess the quality of cross data. So the picture on the right is a group of increment cores. And conceptually, what is happening in Cofecha is that we are taking measurements of the ring widths of all these cores. Then we are creating a chronology, as we discussed yesterday, where we standardize each core and then take the standardized ring width indices and average them together. That makes a chronology. And in Cofecha, if you think about, so in this picture we have 1, 2, 3, we have 9 cores in this picture. So imagine if we were to take 8 cores and make a chronology, and then compare the correlation of the chronology's indices with the indices from the 9th core. So we go 8 to 1 and make that comparison. Then we take a different one out and we calculate the new chronology with 8 and compare it to the 1. And then we take the third one by itself and the fourth one by itself and so on. So each time we're comparing the group minus 1 to that 1. And we do that for every single core, which allows us to assess the correlation of ring width indices of one sample versus the chronology made from all the rest. So that's what that sentence is saying, and the last word that we haven't addressed yet is the word segmented. It does this correlation comparison not only for the overall correlation of all the tree rings, but segment by segment. And the default, the standard length of a segment is 50 years, although you can change that. And it's 50 years that overlap by half, by 25 years. So if a particular core is 200 years long, then we take the first 50 years from years 1 to 50 and compare that to that same time period in the chronology. Then we take the next segment at 25 to 75. Then we take the next segment at 50 to 100. And so each segment is overlapping the one next to it. And by doing this and comparing the correlations, we find periods where the correlation gets worse or gets better. And that helps us focus in on the place where there is some sort of error in the crop stage. So that's why they're in segments. That was a long description in words, but we'll look at examples and then you'll see what the program is doing. So COFECHA helps us note outlier ring measurements, unusually narrow or wide rings that allow us to check cross-stating accuracy. So what this means in practice, we have talked a lot about this feature of marker years, and particularly the narrow ones. We mentioned, and some of you saw in the cross-dating online, or some of you even experimented with the feature called wide rings. And in the graphical thing with the skeleton plots, if you opened up the one called wide rings, you could put notation for rings that were unusually wide. The notation is B for big rings. It's the letter, actually the letter B was written on the graph paper. And so what COFECHA, one of the outputs that it provides for a given core, is it notices rings that are particularly narrow and rings that are particularly wide, and it reports them back to the user. That is of interest to us because when we know our chronology, we recognize that a certain year, for example, where I live, the year 1951 is a narrow ring because there was a drought that started in 1951 and it ended in 1956. So that whole period is kind of narrow, but 1951 and 1956 are particularly narrow. So if I have an increment core from my region and COFECHA comes back and says 1951 is a wide ring, unusually wide compared to all the other 1951s, that could happen. Something could have been different for that particular tree that even though it was a very dry year, it grew okay or even unusually well. But more likely, there's an error in the cross-dating. More likely, that's actually not 1951, it's perhaps 1950 or something else. And so this gives me a clue to investigate, to go back to my sample and look at that year again and say, well, did I make a mistake here? Did I overlook something? Have I dated it wrong? Okay? And a final thing that COFECHA helps us do is identify possible dates for an undated set of tree ring measurements. And this is very much like what we were doing online with the skeleton plot dating online. We had a sample that was 60 years long, and we had no idea where it was. It's not like the samples that we collected in the field here, where we know that the last wood that we can see formed in 2017. Unlike that situation, we just had 0 to 60, and it could be anywhere within hundreds of years. So chronologies like that are called undated, or excuse me, tree ring measurements like that, or samples, are called undated samples, and sometimes they're called floating because they appear to float in time. We don't know, and we don't have any anchor point to say where they are in time. And COFECHA helps us identify potential points, potential dates for those samples. This is often the case when we have dead wood. So if we are sampling from dead trees or from cut stumps or from archaeological samples, it's often the case that we don't know, we don't really have any idea at the starting point where those chronologies are located. All right, what does COFECHA not do? So this, what we discuss on this slide is an important part of dendrochronology. And it's a part of dendrochronology that not everyone in the world sees the same way. So there are some laboratories that view things differently. So I'm going to give you the, what can I call it? The view from the side that dendrochronology requires an experienced person to interpret tree ring data, not just a computer. So COFECHA, this is another quote. These quotations are from the Gracino-Meyer paper. COFECHA does not provide precise accept-reject criteria for making objective decisions to determine whether a series has been cross-dated correctly throughout. That's a very long way of saying the computer cannot cross-date samples. The computer cannot say definitively, yes, this is cross-dated, no, this is not cross-dated. What the computer can do is give you correlation coefficients. It is your responsibility as the dendrochronologist to interpret those correlation coefficients in light of your visual examination of the sample and your knowledge of the chronology. And of course, when you're starting out, you say, well, how do I have any knowledge of the chronology? Because I don't have any knowledge of the chronology. But you gain that knowledge by working with samples, by looking at what others have found, and then by looking at your own samples and beginning to recognize the patterns of tree rings that are influenced by climate in your region. There are some laboratories that move from the field to the scanner to the computer output without a person really looking carefully at the wood. And I think, and the majority of the dendrochronological community thinks that that's not appropriate because it opens the possibility for mistakes. If you have high correlations, then probably your wood is correctly dated. But if you are not confirming that through having an experienced person look at the wood and make decisions about the correct dating, then you have the possibility of error. And we'll look at some examples where you can find some pretty high correlations and be incorrect. And we'll also look at some examples where you can have some fairly low correlations but still be correctly dated. So, the computer cannot cross-date tree rings. Not only with COFECHA, but also with other kinds of dendrochronological software. So, going back to Gracino-Meyer here, the program should not be used as a substitute for visual cross-dating on the wood sample. Instead, the program should be used to check the accuracy of this visual cross-dating on the wood sample. So last comment here again from Gracino-Meyer, the ultimate decision concerning whether or not a tree ring series is dated must lie with the dendrochronologist. COFECHA may be used, however, to assist in deciding to accept or reject, and COFECHA's greatest utility really is helping us find where errors are located and us resolve those errors. This is a quote from Douglas, who says in 1947, to build a chronology, we have to carry dates from tree to tree through comparisons of individual rings by means of ring patterns. Each individual ring has to form its part of a pattern. That pattern is built of individuals, not of averages, and is therefore precise to the individual ring, which is not true of correlation coefficients. So the next part of the sentence, he says, when you recognize a friend, you don't use mere resemblance as in correlation coefficients. You see many details that you are acquainted with. So when you see your friend, in your mind, there's not a scanner that goes, yes, my friend has eyebrows that are the same height as those eyebrows and a nose of this length, and I am now 94% certain that this is my friend. No, you actually recognize the face of your friend. And it may seem like a stretch for those of you who haven't worked with tree rings yet to go from saying that to saying that you can see that in the tree rings, but you can once you start working in detail. Okay, so the software for Cofetia is available at several sites online, but one site that's particularly useful is this one. This is the Tree Ring Lab of Lamont Doherty Earth Observatory, LDEO. And LDEO is part of Columbia University, university in the U.S. So this is one place to go. While we are talking about how you obtain tree ring data, I'm going to pass around a set of papers. Two of them are by Andrew Bunn, and one is by Lara. I guess I don't know what Lara's first name is. It's one of those journals that only prints the initials, so I don't know. These are packages in R that also provide tree ring data, so you can look at those also as we're talking. When you go to this website, it's a little bit hard to see, but most of the programs have two different options. One is called OS X, which is Macintosh, Apple operating system, and the other one is Windows. And it says Windows XP because most of these were written long ago enough that they were written for Windows XP, but they'll also work with other versions of, more modern versions of Windows. So you simply click on the program that you want, and it downloads it, and you can save it. This is what the Cofetia for Windows program looks like. It runs in a small window. It's a pretty simple program, and so it does not install into a directory in your computer. It's not installed as a program. Instead, you copy it to where you want to use it, and then you just click on it to run it. We'll look at that in a moment. The original Cofetia program was this little black window right here, and that was the really old version that we pretty much don't use anymore. The Dendro program library in R, DPLR, is related to the papers that I'm passing around, and Andrew Bunn is the author who has worked to convert these Dendro programs into R packages. And then you can call these libraries and use them in the R setting. So that's most likely the future for most of us, because that's the direction that people are going with statistical analyses and with quantitative analyses in a lot of sciences. Okay, so input data for Cofetia can come from your own tree ring measurements of your own samples. You can also find measurements of tree rings at this website. So this is the International Tree Ring Databank, ITRDB. And ITRDB is a weird enough set of letters that if you search on that in Google, this is the first thing that comes up. International Tree Ring Databank. There are several different data formats. The one that is kind of the most standard and the easiest to use is called the decadal format. And we'll look at examples of this. Sometimes that's also called the Tucson format because it was pioneered by the Tree Ring Lab in Tucson, Arizona, the Laboratory of Tree Ring Research. So you can download chronologies from the Tree Ring Databank, and you can develop your own data by measuring your own dated tree ring samples. So when one runs COFECHA, COFECHA, as we discussed, is going to make a chronology out of the data that you give it. And then it will compare the performance or the correlation of each individual sample to a chronology made of all the rest of the samples. So in order to do that, COFECHA has a number of options for how to make the chronology. So yesterday, for instance, we discussed a lot of these options. We discussed, for instance, that some people can fit a deterministic model, like a negative exponential function, to tree rings, or they can use a spline, an empirical moving average through the data. So in the case of COFECHA, it picks a spline, and that's item number 1 up here. And it says rigidity of spline for filtering, and then to the right it says current values 32. So what that means is that the spline, or the period used for taking a moving average, includes 32 years in every time that it uses a spline to standardize tree ring data. That's the default. So you could change it if you wish. If you, at the bottom of the screen, right here, if you select the number 1, number 1 is for that rigidity of the spline. Current value is 32. So if you select the 1, then it says, what value would you like to use? So if you have a reason why you want to use a longer or shorter value, then you can change it. Similarly, by default, item number 2, the segment length is 50 years with a lag or an overlap of 25 years. That's what we were just talking about, where it uses a 50-year segment, then the next 1 to 50, the next one is 25 to 75, etc. So you could change that. So then you would select number 2, and you would tell it what you would like instead, etc. So all of the things on this, everything on this menu can be changed. Until you have a specific reason why you want to change it, it's useful to know that the defaults are okay. You can simply accept these defaults, and it will give you a good, useful output for looking at your tree ring data. And the most common value of this segment length is 50 years. One of the things that I want to point out, well, 2 of them that I want to point out, number 5, it says correlation critical value 0.3281. So what that means is this is a value of a correlation coefficient. The correlation coefficient is, in statistics, is R. It's the basis for R squared, which is the coefficient of determination. We were talking about that a little bit yesterday, which tells you how much variation is explained in one variable, in a dependent variable by an independent variable. The correlation of value of 0.32 is a reasonably high correlation level. And so the reason that the program is using this value of 0.3281 is that this is a level high enough that it's maybe unlikely to get such a number by chance. So it's a somewhat important correlation coefficient. Notice that I'm avoiding using the word significant. We're not trying to test for statistical significance here. And also, as you will see, you can easily get, when you test the possible correlations of all the places where a tree ring series might fit against a long chronology. You have hundreds of possible places where it might fit because you have hundreds of years in the chronology. You will get many erroneous places that are higher than 0.32. So it's a correlation value that calls our attention to it, but it's not uniquely, it doesn't mean that something is correct or that something is statistically significant. Sounds a little strange, I think. We'll look at examples and then it will make more sense.
It will require developing a new table for it then. Our table for testing the significance.
We're not using, yeah, we don't want to use it in this application.
I have understood, yeah.
You'll see where it comes into play. But the reason that it's important is that when we have correlations that fall above or below this level, the program will do different things. And those things are calling to our attention that we have a correlation unusually low or unusually high. And that calling of attention is called a flag. Like when they say it raises a red flag, means that we notice something. It's a warning or a signal. And that's what this correlation coefficient does. Okay. So rigidity of the spline, segment length. So rigidity of spline, we already said that the 32-year rigidity is okay as a default. Option 2, segment length. We typically go with these segments that are 50 years and overlap by 25 years. So down here on the bottom we have some output where we have a series of segments that are 50 years long and then they overlap each other by 25 years. So for instance we have 1600 to 1649 is a segment. And then the next segment is 1625 to 1674, then 1650 to 1699. And the correlation coefficients that are shown in here, 0.75, 0.8, 0.8, 0.84, 0.77. So that for the first series in this group of tree ring data, 0.75 means that for this core in that segment, the segment that goes from 1625 to 1674 for those 50 years, it has a correlation of 0.75 with all the rest of the tree ring data, the chronology created from the rest of the samples in that data set. A correlation of 0.75 is really good. A correlation of 0.80 is really good. It is very hard to get a correlation of 0.8 by chance. However, it is possible to get a correlation of 0.4 pretty much, or to have it be wrong, you have to be a pretty high likelihood of getting it. So that value of 0.3281 is a relatively low value as a threshold. So when we look at the data for this core, we see high and consistent correlation through all of these segments. It's also worth noting that at the beginning, there might be relatively few other samples to make the chronology, but by the time we're in the middle of the chronology, now there are many other samples that cover this period of the 1700s, the 1800s, and we continue to have a very consistently high correlation of this core compared to all the others. So that's the kind of data that Fulé gives us that lets us assess, lets us believe that that core is in fact correctly dated. Okay, the program does autoregressive modeling by default. We talked about that yesterday. That's taking into account the measured autocorrelation or that persistence or ecological memory that we talked about yesterday. And when we include autoregressive modeling, that just means that our chronologies are more sensitive to interannual climate variability. That's the example, or the way that it works that we talked about yesterday. These other options here are all reasonable, so we usually just leave them alone unless we have a reason to change them. So Cofetia runs by fitting spline and autoregressive modeling and taking logarithms of the data set. By taking logarithms, it helps reduce outliers, so it makes the data more consistent. These detrended series are averaged together to create a master chronology of ring width indices. In this case, using the standardization by difference, so that we have a mean of 0. We have positive and negative values. And we have a stabilized variance such that the value of 1 in the indices is 1 standard deviation. Each series is compared segment by segment with the master, but a master that's created without that series. So it's 1 compared to all the rest. For each series, the correlation coefficient is calculated at the dated position, but then we have more information about series where there is some sort of a low correlation. In those series, we go year by year for 10 years earlier and later. I'll show you an example of that in a minute because it's kind of hard to explain in words right here. But what it does is it helps us focus in on possible problems. An interesting utility of Cofetia is that even if there are errors in the data, even if there are a number of errors in the series being compared, Cofetia is still effective at locating problem segments. This is very useful when we are first developing the chronology, when we're first trying to cross-date or be correctly cross-dating a new data set. Even when there's a lot of errors, the signal tends to override the noise. In this example here, it says even when more than half of the series being tested were incorrectly dated. And the reason is that the errors tend to be random, but the correct dating is correctly dated and bringing in a strong climate signal that helps us find the correct correlation of each sample, even though there's a lot of errors. The Cofetia output is a bunch of kind of gobbledygook like this. We'll have to see how it runs on. I think we can make the screen bigger when we do actual runs of it, so we'll be able to see it better. But it prints out a long text file, basically, that we can look at. All right, so that's an introduction to what Cofetia does. Now let's look at actually using Cofetia with some real tree ring data. And I thought for that we could go ahead and use some data, download some data from the International Tree Ring Databank. So the Tree Ring Databank is part of this larger, let's see if we can increase the size of the screen a little bit. I think that helps. So it's part of this larger paleoclimate data source. And this is a place where researchers around the world have archived paleoclimatology data from all kinds of natural sources or natural archives, including tree rings, ice cores, corals, lake sediments, etc. And so for people working with paleoclimatology or climate reconstructions, they can find all kinds of information here from all around the world. So we have different ways of searching. So if we go to paleoclimatology data search, and we come down to this part, we can choose what data type we want to look at. So this lets you see a variety of different data types. In the fire history category, we're going to talk about that a little bit next week because a lot of the fire data come from tree ring data as well. But if we go down to the bottom of this list, we find tree rings. Let's get rid of the speleotherms. Okay, so we just leave tree rings on there. Because the screen is made so big, this box where the tree rings are is appearing underneath this box, but if you look at it on your own computer, it'll be to the right. But I guess by making the screen bigger, it's pushed it down to the bottom. So there's tree ring, and then we have a lot of different choices of how to choose, how to select our tree ring data. So we could select by investigator and go through this list if we know the scientist who is associated with the data set. In this case, we're going to go with this continent filter. So we go Asia, and if we select here all of India, then we will see all of the tree ring records associated with India. We could also give it latitude, longitude, and elevation coordinates to have it narrow down, or we could use some of these other keywords, but we're not going to do that right now. We could also pick by species and see what's available for different species or times. But the only thing that we have selected is India, so we search, and did it answer? Yeah. So these are the results. So the first thing, which is a very unfortunate thing to notice, is there are only 23 sets of tree ring data for the whole country of India on the International Tree Ring Databank. I know that there is much more research than this in India, and I'm not sure why it's not present on ITRDB. On the first day of the course, Professor Garpoti said that sometimes researchers like to hold on to their data instead of making it public, and maybe that's part of the explanation. Were you looking for something?
Yeah, there are some places which are very near to my place.
Which is it?
Dendroecology. Yeah.
Dendroecology, this here?
Dendroecology.
Okay, let's look at this. Let's look at this data set. So that's India 019. So the way that they label things in here is they have some sort of a code related to the country or the region, and then they have in order of contribution. So that's contribution number 19 of all the Indian chronologies. Just to give an example of the difference in the number of chronologies, I live in the state of Arizona, and one of the chronologies that we use is Arizona 521. So there's a lot more chronologies available from there than there are here. So when we come down, we have, it's named after the person, named after the place, and then it should be named after the species, which I don't know what PCSM is. Picea smithii. Ah, that's interesting. Yeah, Himalayan spruce. Huh. Okay, so let's look a little further through this data set. We have some links to different kinds of metadata. We have a map. Does that map look right? And we have several different files available. So what's in these files are several different chronologies. So there's INDI019.CRN. A CRN file, or a chronology file, is a type of ASCII file. ASCII just means plain text, right? I don't know if everyone's familiar with that expression, ASCII. It's just a plain text file that contains all the information for this chronology. So as we have discussed, if it's a chronology, that means it's already the standardized, averaged chronology information. Then there's an A and an R chronology. So it's most likely that this is an R stand chronology and this is a residual chronology. We talked about those a little bit yesterday. Those are two different ways of constructing a chronology. The first one that doesn't have any letter after it is most likely the standardized chronology, just the, the standard chronology, just the average of all those ring width indices without anything else being done to it. This
Just repeat, A stands for?
A is probably an R stand chronology. I'm not sure because I didn't create these, but I think that's what their coding means. A is an R stand chronology and R is a residual chronology. The residual one is when you've taken out, or you've tried to take out the autoregression. And so the R chronology is probably the one that is the most sensitive to year-to-year variation. But we're going to, there's also a file here called correlation stats. And I don't want to open that yet because I want us to make our own chronology and then we'll compare it to what that chronology stats file says. So we're going to come to the bottom value here called raw measurements. And this is the original tree ring measurements. So let's click on this and see if this stuff works. It's not working the way I want it to work. So I want to show you, let's look at a different chronology because I already looked at one on here and I want to use a particular kind of measurements file because it's the easiest to see. And then we'll come back to that one. Because that one is in a different format and it's a format that you can't clearly see what's going on with it. Where did the, let's see. I made the screen so large that you can't see anything anymore. Let's make it a little smaller. There's tree ring. Here's India. Let's search again. And this time, so they're organized here alphabetically by the contributor. So let's look at this one. Click on it. Okay. So this is AB's Hindro, West Himalayan fir. And if we do this one, we have a file called Indy 001, this is the very first chronology, or the first tree ring data set uploaded from India, .rwl. The RWL, RW means ring width, and these are ring width measurement files. But the format of this one is going to be different than the one we just looked at, because I already checked it. So this one is easier for us to use right now. I just want to call your attention to, there's two below it called E and L. That's early wood measurements and late wood measurements. Then there's two called N and X, and I don't know what those are, so you can investigate them and see. And now if we click on, what? Why is it
This
doing that?
is the largest key size. It was coming all right in the laptop when I ejected yesterday.
Maybe so. Let's make it even a little smaller. Let's try one more time. I may have been incorrect about what I thought I had. Okay. We will, for a moment, leave India. Let's go back to Arizona and let's look at this one. Okay. So this is an example of tree ring measurements in a decadal format. And I'm not sure what I was doing wrong on the combination of the search or the spreadsheet, but I was able to look at that exact same Hughes chronology in the 001 this morning, and it opened this way. So somehow I'm doing something wrong. I don't know. But it doesn't matter. This is what we look at. So the first thing in this file is some header lines that are simply describing the location. It has a very abbreviated latitude, longitude. It has the early date and the end date of this data set. This is Pinus ponderosa, so P-I-P-O. I thought it was interesting when we looked at the ITRDB site that for Picea, instead of P-I, they put P-C. That's why I didn't recognize what species it was going to be. P-C, I don't know what P-C is. But I guess because there's so many pines that they wanted to separate out the P-I and the Picea. Okay, so this describes, and this Donald A. Graybill is the person who created this chronology. This is one of the chronologies that we have in Arizona. Then we have our first tree. So this is GPN011. That's an identifier of the tree. Then we have 1640. That is the year 1640. And then we have 10 numbers. Those 10 numbers are the 10 ring width measurements, in this case in hundredths of millimeters, of the year 1640, 1641, let's deal with this, 1642, 43, 4, 5, 6, 7, 8, 9, and then we jump to the next line, and here's the measurement for 1650, 1651, 52, etc. So in the year 1651 is the first one, well, it's not the first one, let's see, this is the first one, 1641, 2, 3, 4, 5. 1645, now we have a ring that's bigger than a millimeter. It's 1.01 millimeters. Does everybody see that? So this is just a big list of numbers, but these numbers actually translate into the actual measured ring widths of that tree sample in that year. So this decadal format is kind of nice to look at because you can see what's going on. You could put it into a spreadsheet or something and manipulate it.
How
Yeah.
do you know that it is a millimeter and not some other unit?
Because it is in millimeters, so it's not a good answer.
Is it
But
standard, like for
it's
India
a
also,
standard,
is this-
yeah. However, what you will see is, see how these numbers are quite small, 48, 20, etc. These were measured in hundredths of millimeters. What you would see nowadays is this would be written as 480 because it would be measured in thousandths of millimeters. And this number, 101, would be 1010. It would have 4 digits. Another way to tell the difference in that precision is that the ending symbol of this tree ring, of this tree, is a 999. So if we come to the decade 1980, we have the year, excuse me, where are we? 1980, 81, 82, 83, 84, 85, 86, 87, and then it says 999. And the 999 is the code to say end of file for that tree. And then it goes to the next tree, which is GPN 012. That starts in 1653, and we have 53, 54, 55, 56, 57, 58, 59, and then it goes to 1660. So our first tree, by coincidence, began in a decadal year. It began in the year 1640. But you notice that the second tree did not begin in a decade. It began in 1653, and thus it has fewer values, and it has like this incomplete line right here, because that's the end of, that's a 9, and then it goes to a 0. Does that make sense? So the modern day code for this thing, instead of 999, is negative 4 nines, negative 9999. And that will correspond to a file that will have bigger numbers in it, basically, because it's being measured with a higher precision instrument. Current ones that we looked at online yesterday from Velmex and Lintab all measure to 0.001 millimeters. Okay, so the fact that you can see these numbers and you can relate them to an exact year and an exact sample is an advantage. The reason that it's done in this way with these ASCII files, these text files, is that this stuff was originally computerized in the 1980s. And so it's a very old kind of a format. There is another format called compact that used less memory space than this. This uses a certain amount of space because there's spaces between these values and there's repetition of the code, for instance. So they created a format called compact that made the file even smaller. The problem is we can't read it. I mean, you could read it if you knew the underlying logic of how it was made more compact, but you can't read it easily in front of you like you can with these numbers. And that was done to save memory space because back in those days, even a file of a few kilobytes was using up a lot of the computer memory that they had available. Nowadays, obviously, a file like this is a meaningless amount of memory.
What is this at top 1550, 1987?
So 1987 is the last year in the whole data set.
Okay.
And 1550 is the first year of the oldest tree.
Okay, so at the bottom, you might be having one of the records of 1500.
Somewhere in here is a tree that starts in the year 1550.
Okay.
It's not necessarily at the bottom because the ordering...
Somewhere in.
Yeah, somewhere in there. The ordering is simply by the number.
Yeah.
And the number is probably arbitrary. It's just the first tree that they included down to the last tree that they included of the way they sampled. Okay, so for instance, here's a tree ending at 999. And then we have this tree GP9, 342, 1813, 14, 15, 16, 17, 18, 19, and then it skips to 18, jumps to 1820. Okay, so this is called the decadal format or the Tucson format, and we have a bunch of trees listed in here in order. They're just in this vertical order. So let's run Profecha on this. I did just try this, so I hope it runs okay. All right, so when you open Profecha, it opens in this little window like this. You can expand this window and you can expand this window. But what I don't know if we have any way of doing is making this bigger. I don't think we have a control over that.
Control plus.
Plus. Control plus.
I think it's not good.
No. Any other ideas? Does anyone have experience with? If we change the screen resolution, does that?
Windows plus, just try Windows P and plus. Window P and plus.
Okay, let's try that. Ah. Yeah. I don't know. Now it's... My only choice seems to be 100 or 200.
Frequency different.
Okay, sorry. All right. So, I mean, are you guys able to see that? That just made it disappear now. Okay, all right. I think we can look at the output file in Windows, I mean in Word, and then we can open it up bigger. So let's try that. So you come in and tell it what the name of your job is going to be. You just give it a name for this run. So I'm going to call it T1. It asks for the cross-dated tree ring series. This is a series that you're using to create, that you're using because you think that it already is cross-dated, or you know that it already is cross-dated. So I'm going to put in AC521.rw, and it found that file because they're in the same directory. This is some really old computer technology in terms of how Windows works. If the Cofetia executable is in the same directory as your files, then it can find it. So, so we accept it and we say that that is the correct file, and it asks format is measurements, correct? And it is measurements, so we accept that. So there are 67 series in here. Cofetia is saying the start date is 1540, and the other one said 1550, right? But it's saying it because there must be a tree that starts in 1540. So, I don't know. Covers 448 years. Next it asks if we have an undated tree ring file. This is something we're going to look at next, but for right now we're going to skip it. But what this would allow us to do, if I were working on a new set of measured files and I wanted to check them, I could put them in here, either one tree at a time or a whole list of trees. And it'll compare those files to the chronology. But for right now, I'm going to skip that. Now we get to these options that we discussed, the spline and the segment length and things like that, and I'm just going to skip those. Now it does this run, it gives me a little printout, and it's finished. So I hit exit. I don't need to save anything at that point because it has saved this output file. So let's see if I can open this with... Why did you do that? Open with Word. All right. So when you open it with Word, you have to change the orientation to landscape, and you have to change the font. So we change the font to this font called Courier. We change the font size to 8, and then it fits on the page. It has to be a non-proportional font because otherwise it won't work. All right, and now I can finally make the screen bigger, so that helps. So this gives me the output then. So in the output it tells me that this is the file that we used, AZ521. It has printed all of these different segments, all these different contents. It repeats the run control options. So the things like the spline, the segments, and all that stuff, it tells us. And now it starts to give us information about the file. So the file runs from 1540 to 1987. It lists absent years, years that had a 0 value. These are dates where the dendrochronologist assigned a 0 because the ring was missing. We talked about this over the last couple days of how we can have the anatomy of the wood is such that the growth of the tree is such that a ring was locally absent or maybe completely absent in a particular year. The dendrochronologist identified this by matching the patterns on either side of this missing ring, and they realized that a certain year, in this first case the year 1897, or in other cases 1928 or 1542, were absent. So here's all the absent rings listed by series. Most of these absent rings are going to be in years that are known to be very dry. So for instance, I had mentioned to you that 1951 is a pretty dry year in this region, and there's 1951. 1971 and 74, these are all years that are quite dry. There are a total in this data set of 144 absent rings, but that only is 1% of all the tree rings in these series. So now we move along, and the computer makes us a kind of time plot of the tree ring series. So we see, for instance, that tree number 1 goes from 1640 to 1987. That's the tree that we already looked at in the data file. And so it draws this little line to just kind of give you a visual idea of which trees are overlapping. You see that many of the trees are young, but some of the trees are quite old and go back a long ways in time. Okay, so now we come along. Let's find where we are. Okay, time plot continues. All right. The next part of the output is what's called the master dating series. And this is giving us a list of years. So let's look at this part of it right here. It's giving us a list of years, then it has values, and then it has number, which is what NO means, and it has absent. So, in the year 1550, it has a value of 2.334. Then in 1551, 0.616. Then negative 0.032. See these values? So what these values mean is this is the chronology value in these years. This is a printout of the master chronology. However, in the year 1550, there was only one tree in the chronology. So we're not going to place a lot of importance on that. But if we jump over here, we're now in the 1600s. Now we have 10 trees, 11 trees. In the 1650s, we have 15 trees, 16 trees. So these values are much more reliable. And these are the actual chronology values. Because of the type of standardization done here, the mean is 0. So that means that negative numbers are very small ring width index values, which would correspond on average to really very small rings. Positive numbers are large values. Numbers right around 0 are right in the middle. And thus we see that the year 1600 is probably was a very dry year. This is the same chronology from which I had pulled individual trees in the lecture we had yesterday. So when we were talking about standardizing and we had the estimated growth curve, the red line, and we looked at the year 1600, it was a big drop on that graph. Well, here's what that translated to in terms of its chronology value. Negative 2.337. And for the first time we see something in this column, that means that out of the 10 samples in the year 1600, 2 of them had an absent ring in the year 1600. So 1600 was a dry year. On the other hand, 1609 is a somewhat wet year, wetter than average.
Something big detailing on these values, that if mean is 0,
Mm-hmm.
what does that mean? Mean 0 and then the negative values.
So it means that in the type of standardization that we did, when we put a growth curve through the tree ring growth, we subtracted the difference. So if the tree ring grew more than the average line, it's a positive value. And if the tree ring grew less than the average line, it's a negative value.
Okay.
And when all those were averaged together, the year 1600 had a very negative value.
Okay.
That's what that means. Yeah.
Okay, that is a middle point basically. 0 is the middle point.
0 is the midpoint. Yeah. If we move along, here is 1951. What did we just do? Okay. So there's the year 1951. And 1951 also has a very small value. Recall that we said that it was set up such that the standardization worked so that there was the value plus or minus 1 is plus or minus 1 standard deviation. So this is minus 2.2 standard deviations. So in normally distributed data, that puts you around 95% to 99% at the extreme of the data set. So we have 66 samples in 1951. That's a very robust data set. We have a lot of depth. We have, on average, very dry conditions that year, and we have 3 samples that were missing a ring, that had an absent ring or a value of 0 in 1951. 1956, I mentioned, was the end of that drought, and also a very strong negative value there. So you can see how the chronology created from these 67 samples turns into this kind of a representation. The next thing that Kolfecha gives you is a graphical representation of this, called the master bar plot. And the master bar plot is a way to get a visual representation of what the numbers mean. The visual representation works like this. In each year, it says year, and then it says relative value. So in each year, like the year 1650, if 1650, let's look at 1701. 1701 is followed by a medium length line of dashes, and then the ampersand symbol. This symbol is used for the average condition. The year 1701 was an average year. In terms of its value, in the chronology, it's going to have a value around 0 because it's neither positive nor negative. If we have a year with a greater than average value in the chronology, we give it a capital letter, like this capital A or this capital E. And we give it also a line, and if it's very close to the middle, it's an A. But if it's farther from the middle, it's a B or a C or a D or an E. As we move down the alphabet with capital letters, we get a bigger and bigger letter, or a letter, that is farther away from A, and we get a longer and longer line. The lines have a maximum because there's only so much space in the column. But like the year 1709 has a capital E, and it has quite a long line to the right. That means that was a pretty big year in the chronology. Again, so when we've converted everything to ring width indices, we have, on average in 1709, a pretty big year. In contrast, look at 1703. Now we have lowercase letters. Lowercase letters mean they're smaller than average, and the line disappears. Like a lowercase c just has 1 dash, h has no dash at all. Here's a year that is a notable drought year in our region, 1654. It's a lowercase I. So I is a long way down the alphabet. It's a long way away from A, and because it's lowercase, we're using that to mean smaller and smaller. So if I wanted to make a list of marker years from this chronology, I would look for years like this. And look at 1600. Remember we said 1600 was a very small year? Here it's a lowercase I. So I would note the year 1600, the year 1654. I probably wouldn't note the year 1652 or 53. They are smaller than average, but they're quite close to A. They're not much smaller. So just like with the skeleton plot, when we focused on the really narrow years and we made a line to indicate that, that's what this master bar plot is trying to do for us. It's trying to provide us with that information. In the R version of this program,
simply looking visually and interpreting it.
Yeah. In the R version of this program, it will make a little computerized skeleton plot, and it'll show strong lines in the places where something like this I shows up. Let's look at the 1950s. Let's see.
1951.
Here's the 1500s. Sorry, my eye. So 1951 is also an I. And And you recall that was also a very narrow year. So this is an important clue that we get from the Cofetia output that allows us to detect these marker years in our environment. Okay. Do you guys know if the tea is outside? Did you take a look and see if the tea is ready? It is?
It is.
Okay, let's take a break and we'll go have tea and then we'll come back and finish this up and then sand some samples. Oh, thank you. There's an inch. While we finish up, I have one more paper that I'd like to pass around. This is by Professor Yadav from the Tree-Ring Laboratory, the Birbal Sadi Institute of Paleobotany. And Professor Yadav is a dendrochronologist who has done many studies in India. This is a tree-ring-based reconstruction of drought using the Palmer Drought Severity Index that we talked about a little bit the other day for the Western Himalaya. So, potentially something of interest to some of you for your presentations, and just good to start thinking about dendrochronology in India. Okay, so we're going to finish up this discussion of the outputs of Cofetia. And when we get to the end of this, we're going to set up our sanding machines. We have an extension cord, and we'll try to run the power out here on the balcony and then sand our samples. Okay? All right. So we left off with talking about this master bar plot, this kind of visual representation that particularly helps us find the marker years in chronology. And that's a useful feature of Cofetia, something that is helpful to us. Okay, now we are in the part with this idea of testing the correlation segment by segment of all the samples that went into this chronology. So here we have sample number 1. I keep grabbing things by mistake with the mouse. So we have sample number 1. As we saw in the raw data, it begins in 1640, ends in 1987. So since it starts in 1640, the first presence of this species is in this segment right here. There's nothing in the previous ones because the sample wasn't there then. It had actually overlapped this by 9 years, but it has to be present in the whole segment in order to be useful, or at least the majority of the segment. So then if we go to the right, we see those quite high values of correlation coefficients, segment by segment. There is a decline right here, but the value is still reasonably high. And then the value comes back up again a little bit later. So and you notice as we go through this table that most of the cores in here have really quite high correlation coefficients. Does everybody see that? A lot of 0.7, 0.8. The lower values might be 0.5, 0.6. So they're quite high. At the bottom, once we get all the way to the bottom, we have the correlations for... At the bottom, we have the correlations by segment on average for the whole data set. And again, those are very high values all the way across. Okay? That's because this is a well-dated chronology. The trees, the 67 trees that Graybill put into this chronology are all cross-dated correctly, and they're also quite sensitive. So in making this collection in the 1980s, Donald Graybill was visiting this area with some of the perspective that we've been talking about in the past several days. He was specifically looking for trees that would be sensitive to climate, that did not have a lot of evidence of other ecological factors that could cause their ring series to be influenced by different things. He was trying to find ones that would date very well with each other and reflect the regional climate. And he was successful. These are the results of that with these very high correlations. If he found some trees in his data set that were correctly dated but did not correlate well, then that would mean that those trees were probably being influenced by some other factor. Maybe disturbances, disease, injuries, things like that. So he could simply remove those trees from his data set. When he is constructing a chronology, mainly for the reasons of climatic inferences, then he can feel free to discard the samples that don't date well. In contrast, we'll talk more about this next week, when we're doing an ecological study, the tree and what happened to the tree, its history as reflected in its tree rings, is actually the thing that we're studying, not the climate. So we may have trees with much lower correlations than this. As long as they are correctly dated, we may still keep them in our series. So for instance, I work with a lot of fire-scarred trees, and I'll show you more about that next week. And those trees have very distorted growing patterns. They often have much lower correlations. Instead of 0.7 or 0.8, it might be 0.4, 0.5 on a lot of these segments. But my question of interest has to do with the trees, not with trying to get a high correlation. I'm mentioning this because in many studies that you may do, if you are studying the dynamics of a forest stand, if you're trying to look at how growth occurred in the forest, etc., then your trees are not necessarily going to be super reflective of the climate, because that's not the question you may be asking. And thus you cannot always expect to see these kinds of excellent correlation coefficients. I don't think there's a single segment. Here's a flag. Okay, so we can look at this flag. So here we have a correlation of 0.44, but then there's a letter that appears, letter B. And letter A and letter B are called flags. They call our attention to something about this tree. And the 4,4 is kind of a low correlation, but it's not tremendously low. Here's 0.48, here's 0.45, and those don't have any letters by them. The reason that flag is there, the reason the B is there, is not because the correlation is considered too low. The threshold for calling it too low is the 0.3281. If it was below that, then it would have an A next to it. But it's above that. However, what this B flag means is that somewhere within 10 years on either side of that date, there's a better correlation. So it's calling our attention to that. It says where that segment is dated currently, the correlation is 0.44. But somewhere in plus or minus 10 years, there's a better correlation. So you should just look at that. Doesn't mean it's wrong, it just means you should look at it. Okay. The other thing that we should note is that that's in the very first segment. So there's only one other tree. There's only two trees that are correlating with each other at that point. So that's not a very robust part of the data. So that was tree number 13. So we'll look at that in a little more detail. So for each series with potential problems, the following diagnostics may appear. It will show correlations associated with moving each segment 10 years earlier or 10 years later. I'll show you what that looks like. The effect of data values that most lower or raise correlation. This is where we would identify, for instance, that normally a certain year, like 1951, is very narrow, but on this one sample, it is not narrow at all. Why is that? That's a question you could ask. And presence of absent rings, statistical outliers for that year, and year-to-year changes very different. Okay, so when we come into this section, we have on the right-hand side it lists series number 1, and then here's that series GPN 011 1640 1987. it tells us the entire series has an overall correlation of 0.78, which is excellent. It points out that certain years are unusually low in correlation, or I realize right now I don't remember what that number refers to, so I don't want to call it correlation. I'm not sure what that number refers to. So we're going to have to skip that for a moment. And it lists all the absent rings found in that tree. It also points out that 2 of the absent rings are not usually narrow. It is possible for a tree to not form a ring in any particular year, but it's much more likely to happen in years that are the marker years, the narrow years, because those were drought years. So it's calling our attention to the year 1897, for instance. So we move on to the second series. Again, it tells us what the absent rings are. Third series, and so on. So let's go to series number 13, which is where we saw that flag. So here's series 13. Now we see something a little bit different. So that segment was this segment 1570 to 1619. How did I get rid of the zoom? Oh my goodness. I'm sorry. What in the world? Okay. So we're in Korea new. I have to stop using the mouse for this. All right. I think it'll show it all right at 150 magnification, but not at 200. That's still not showing it. Let's see if it'll let me zoom a little bit. Okay, I don't know why now it won't let me zoom. Because every time I try to zoom, it changes the layout on the screen. Sorry?
Sliders they call it. There is, you can use the slider which is at the bottom right hand side. So from there you can, yeah.
Thank you. No, but it's still not right because it's moving it off the screen. (110% seems to be the most we can do. Okay. So what has happened, this is the segment that we saw the flag on. So now we have a new graphic here that goes from -10, -9, down to 0, and then +1 up to +10. So there are 21 years shown here. 0 is the position where this segment is currently dated. And in that position, we have a correlation with the master chronology, but really with just one other sample, of 0.44. The reason for the flag, if we look along these other potential correlations, is the computer is saying, if you were to move it 10 years forward, +10, if you were to say that the year 1540 is actually the year 1550, then this segment would date at 0.45. This is an early indication of a point I was trying to make, that correlation coefficients in and of themselves, especially for one segment at a time, cannot prove that something is or isn't correctly dated. There is the core as a whole has a very high correlation. The effect of the core overall is 0.733. The core is correctly dated. There is not a 10-year error in one segment of the core coupled with some kind of magical loss of those 10 years somewhere else. This is by chance that if you move segments around and try enough different combinations, eventually by chance you will get some fairly high correlations. And that's why it's necessary to have kind of a broader context of looking at these statistical results. And that's why there's not just simply a threshold of saying if it's this correlation, then it must be correctly dated, because that's not how it works. But conceptually, do you see what the computer's doing here? It's testing. Whenever there's one of these flags, it says, okay, possibly there's an error. If we were to move this segment back 1 year, back 2 years, back 3 years, what would happen? And the reason that it's plus or minus 10 is that the most common type of error in dating is ought to be off by 1 year. That you have accidentally accepted a false ring or overlooked a missing ring and not accounted for it correctly in your dating. So looking within plus or minus 10 years helps you pick up most of the errors.
Excuse me?
Yeah.
Does that mean that after 10 years or within decades, we are getting the same correlation as we have got in 0 years, what we are considering 0?
Mm-hmm.
Like after 10 years, 0.45, at 0 it is 0.44, almost same.
Yep.
Suppose, so does that indicates that at the same decadal cycle, we are getting the almost same correlation? Does that flag indicates?
In this case, it's a 10-year space, but that's not, what you should not do is try to draw too much interpretation from it, because remember, this is the first segment in the series, and it only matches one other core. Does that make sense? Because these are the two oldest trees in the whole data set, and this is in the oldest part of the oldest trees. So what it's really due to is the fact that we have almost no sample depth. If we had 50 or 60 samples at that time, then we would have a much more robust conclusion. If we saw the same numbers, then we could say, oh, maybe there's some phenomenon going here, some kind of 10-year cycle that we need to investigate. But right now, it's more like chance. Okay, so most of these, because there are not other flags, most of the information here is simply reporting the average correlation and the absent rings and so on for the rest of these samples. We work our way down towards the bottom. And we have a summary. So these are descriptive statistics of the whole data set. And we list every tree, its beginning and ending date, number of years, number of segments, number of flags, and the only flag is that one for tree number 13. And then we have we have other information related to the mean measurement, which is in in the original units in millimeters. We have correlation with the master chronology. We have the statistic we talked about called sensitivity, which is a useful statistic when we're trying to see how responsive a certain species or the trees in a certain site are to variations in climate. So it's we find more sensitive trees in places that are rocky, have poor soil, things like that. So all that information is summarized for all the trees, and then we are at the end of our chronology. So this chronology with 67 trees in it had 13,740 tree rings. All right. So let's try one other thing with this, and then we'll move to doing our, let's see if I can, no, see that saved in some kind of HTML file. Let's try another one. I don't know why that's happening. It was, so that first file that I was trying to get to Hughes with the Indy001, I was able to download this morning, but I don't have it on the disk, unfortunately. Well, let's see what this, let's see if this actually saves something. I don't know if Cofecha can open that. Let's see. All right. Well, there was one more thing that I wanted to show you with Cofecha, but we can do that on another day. Because I don't know where the. Oh, okay. Let's try one more time on the website. Try a different place than in there and see if that helps. meeting windows.
These are
Yeah. Okay, so this worked this time. So this is the last thing I want to show you with FHA. So we, in our first run through, we took this data set called AZ521, had 67 trees in it, and we created, or COFECHA, took those default settings, created chronologies, compared each tree against the rest of them, and showed us that they were very highly correlated. We have really no evidence of any kind of problem or incorrect dating, except that one flag, which I think there's too little evidence to say anything about because it's only 2 trees that are dated compared to each other. Okay? Now what I've done is taken that same chronology, AZ521, and I once again put it into COFECHA and called it the dated series. So COFECHA has done all of the things that we just did. Then we put in a second data file called File of Undated Series, which is a second ring width file. And that ring width file comes from a place that is, probably 50 kilometers or so away from where the first chronology was constructed. Same species. So what the program does when you give it a second file is it takes the second file and tree by tree, it compares it to the chronology from the first file. So if I feel that the 521 chronology, now that's a good chronology, I believe that that's correct. Now I have new samples and I want to check if I have dated them correctly. So that's essentially what we're doing here. So we go through this file and it has all the same features that we saw. It has the chronology data, it has that master bar plot, all these correlations by series. We go on and on. This is what we just looked at. We get to the end and we have those descriptive statistics for this whole file. And in the case of the previous version, it ended right there. That was the end. But now we have a new section called Part 8. And it's called Adjustments for Undated Series. So now, I have a new series. Oh, it would be so nice if I could make this bigger. I don't understand why it worked once and then it won't work anymore. But it won't. Problem is that if I zoom in on one segment of it, it changes the formatting of the page and it starts pushing things over. There's something different about the way we zoomed the first time. I can't understand why. So now we have the first tree in our second data set. These are the trees that we want to test against the chronology. This is the first segment from those trees, the second segment, the third segment, the fourth segment, etc. Now the computer tells us that if we look at the highest correlation of that segment, the highest correlation is when it says add 0, and the correlation is 0.67. Add 0 means don't move the date. Keep the date exactly as it is. So that first segment of that tree is 1842 to 1891. And where it is dated, it correlates with those years in the master chronology at 0.67. If we moved it 82 years back, it would correlate at 0.41. If we moved it 279 years back, it would correlate at 0.39. If we moved it 42 years back, it would correlate at 0.38. If we moved it 41 years forward, it would correlate at 0.37. So in other words, it's listing 11 possible options in the order of the best correlation. We notice that for every single segment, the 0 lines up in the best spot. That makes sense because both of these chronologies, or both of these data sets are actually correctly cross-dated. The only thing that would prevent them from correlating highly is if there are some regional differences from one site to another. We do notice that the correlation coefficients here are a little bit lower than the internal correlations of Graybill's data set. Remember, he had a lot of 0.7, 0.8. Here we have 0.67, 0.68, 0.54, 0.56, and 0.7. And it's the same species, so that's probably just the fact that when they're spatially separated from each other by 50 or so kilometers, they're not going to have an equivalent response to climate. Another thing that we can learn is that if we look at the second column here, we have some reasonably high correlations. This one is 0.47. In the third column, we have a correlation of 0.46. So in other words, if you take a segment of 50 years of tree rings and you slide it back and forth against 450 years of possible tree ring records, there are many places where those numbers are going to correlate reasonably well. There are many wrong positions that still have some decent amount of correlation. And so this is part of the reason why a simple correlation coefficient is not a yes or no answer to whether something is cross-dated. But something that is very strong evidence of good cross-dating is this fact that they all line up. And they all line up in the position where they are dated in that original data set. Let's see if there's any differences. So here's an interesting example. This tree, we start off with 0.58, but in the next segment we get a minus 131.41, plus 126.40. We do have zeros showing up, but they have relatively low correlations, 0.37, 0.38, and then we come back to a pretty good set of zeros all lining up. Now, if this was a data set that we had not worked with yet, we would want to look back at that core and see if there might be some problems with it. But knowing that both of these data sets are in fact correctly dated, that is really showing us the weakness of the correlation from one place to another place. This tree is not correlating as well as it could because it's in a different place and has experienced a somewhat different climatic pattern. The next one down is showing that same kind of a thing. Typically when you have problems in dating, you're not going to have problems in dating that tell you to go minus 40, plus 120, minus 310. You didn't lose 300 years, or even 40 years. When you find errors, they're going to be plus 1, plus 2, minus 1, minus 2. Those are the most common types of errors to find, and they're related to those false and missing rings. So this Cofetia here does this process for all of these rings, all of these trees, excuse me. And so this tool of being able to compare your undated or unconfirmed dated samples against a well-known chronology, this is an extremely useful tool. And if you were to find that there are some places where your dating is correlating well in the dated position, but then you have a -1, another -1, another -1, then something has happened. You've taken on an extra ring, it pushed you 1 year forward, and you need to find that ring and remove it, a false ring, to bring your series into alignment. At that point, you might want to rerun the program, and instead of having 50-year segments, you might want to have 20-year segments, because that way you can zoom in a little bit closer on where the source of error might be located. That's an example of where you might want to change the defaults on Cofetia. Okay. Any questions on the use of Cofetia? For those of you who are not going to be working with tree rings anytime soon, this is, I hope that you could see how this worked and you can see why it's useful, but then you're going to forget the details right away because, they don't matter. But if you are actually working with a tree ring data set, or if you come to it in the future, then you will find that this kind of analysis is extremely important. This is what helps us verify our cross-dating if it's correct, and it helps us find errors when it's not correct. It's a very, very powerful tool. One of the things that is sort of a trade-off in the tree ring community is we have certain programs that look very nice. They run, they look a lot more sophisticated than just a printout of a text file, and they make nice graphics and things like that, but they cost a lot of money. And then we have these other programs that are free, and they make little text files like this. But what's running inside of them is basically the same thing. So if you want to make your graphics in some other way and not pay $10,000 for a pretty graph, then this free software is giving you the power of this statistical analysis. And the R version makes somewhat better graphs, somewhat better output.
In your descriptive statistics, there are two columns. One is multiple columns, but broad category, filtered and unfiltered data.
So let's see. The filtered and unfiltered data is referring to the raw measurements are the unfiltered, and the ring width indices are the filtered. So it's showing you, under unfiltered, it's showing you the mean and the maximum measurement encountered on the tree rings of that core in actual millimeters, and their standard deviations, and their autocorrelation, average autocorrelation coefficient, and sensitivity. And then in the filtered data, it's showing you the maximum value in terms of the tree ring index. This is now converted to an index. And the standard deviation of the indices and the autocorrelation. One thing you can notice is the autocorrelation is almost gone because the autocorrelation was removed. So unfiltered is before standardization, and filtered is after standardization. Any other questions or comments? Are there any of you who have experience using Cofetia? Did you use Cofetia? What kinds of applications did you have? What sort of species, what kind of project were you doing? Okay. And did you find it helpful? Were you able to help detect errors and things like that? All right. Hello.
How are you?
I'm doing well. We are just about ready to transition to the samples in a moment. Okay. Anything else on Cofetia? All right. So we're going to transition to surfacing our samples, and this is guideline from a colleague of mine, Don Normandin. And this has some information that we should look at related to sampling and just related to some of the general things associated with working with the wood samples. So at the top, he talks about mounting the sample. We talked about all these things yesterday when we mounted our samples. We have to label the core mount. The fibers need to be vertical. So insofar as possible, that was our goal yesterday, to have vertical fibers. So once the samples are mounted, then we have to use tools to surface the samples. So these are some of the safety rules for the wood shop that we have at our university.
Should be globalized.
All right. I'm not sure I understand. I don't understand what you guys are seeing this morning. But when we work with the shop equipment, so we have sanding machines, and which is what we have with us now. We also have a number of saws. So the saws are used for the bigger wood samples to cut them down, make a smooth surface, and then we sand that smooth surface. So all of these tools are quite dangerous, and it's for that reason that long hair, anything that is hanging down or encumbering, especially your hands, is a problem, or they could catch in a machine. So I am not a person who has long hair, but if I had long hair and I'm leaning over a machine and the machine catches my hair, then I would be in problem.
Yeah.
Fortunately, that won't happen to me.
Yeah.
But it could happen to those people fortunate enough to have long hair. Similarly, if you had, necklaces or something, or bracelets on your arms hanging down, shoes that were unsafe. The issue about the gloves is interesting because it seems counterintuitive to a lot of people, because you feel like your hands are better protected in gloves, but actually they're not, because the glove is extra fabric. If it gets caught, it's taking your hand with it. Your hand can't get out of the glove fast enough. So it's better to not wear gloves. And then you don't want to wear very loose clothing or have, big shirt sleeve openings or something like that. Okay. Some of the equipment that we use, we have a band saw. So this is a saw that the blade is a large band. It goes over two big wheels, and it can cut very large segments. It has an open space like this where the wood can pass through. Then we have a table-mounted saw. A 16-inch blade is about a 45-centimeter circular blade. That's a huge blade on a table saw. So it's a very, very powerful table saw that we use. And then we have sanders. The sander mentioned here is very similar to the one that we're going to use today. So these are called belt sanders because they have a belt of sandpaper that fits in the machine and that the machine spins. They're used for sanding large areas of wood. So you can get a lot of work done with one of these belt sanders. And then we also have a smaller sander here with us. It's called a finishing sander that we will experiment with a little bit to try and get the final, or close to the final surface on the wood. So the way that we use the sander is we have the sander, here it is right here. Let's pull it out. Thank you. The sander looks like this. This is the sanding belt. By opening this lever, it takes the tension off of these rollers and allows us to take the belt out and put another belt on. The belts can be of different grits, so you can have a very rough grit. This is a quite rough sandpaper here. This is what you would use at the beginning. And then you have finer grits after that. We have this dust collector right here that helps reduce the dust the sander produces. Yeah, thank you. And then this is the smaller finishing sander. You open up some edges here and put the sandpaper on this surface, and then you tuck it under the edge and close the clamp down on it. And the finishing sander vibrates and produces a sanding in that way. And these are both really nice ones that JNU has purchased, and we are going to try it out. So the key things with the sander, typically for working with increment cores, we press the trigger in and we use this trigger lock. That means that it's locked on, so it is continuously running. When we turn it upside down, and the sander is designed to be flat like this. So when we turn it upside down, it provides a flat surface, but it moves very, very fast. It moves in this direction. So we can come with an increment core that we hold with our fingers far away from the bottom side of it, and we sand it like this. In order to do this well, we need to have the sander not move. I think we're going to be okay with that out here on the concrete. We need to not ever have anybody sitting here, because what happens if I let go? This shoots like a bullet, and it goes in that direction. So not only not sitting here, but not sitting there, and not sitting for a long ways down from the sander. When we work in the wood shop, we have many saws. And the saws are frightening to people because they're very, very powerful, and you can tell that the saw blade is very sharp. You know, you can easily envision having an accident. And so people are very respectful of saws. And in all the years that we have worked in this wood shop, we've never had any accidents with our saws. We've had several accidents with sanders because the sanders seem more friendly. They're sort of easy. You know, they don't have teeth that are biting you. But you can get your finger caught in the sander. And when that happens, it's a really very bad injury. It's an abrasion injury that would be a terrible thing. So we don't want that to happen. So what we're going to do now is set this up, and we're going to test it out with some of our cores and see how it works. And if everything's working okay, then people can be invited to come up and give it a shot. And then we'll test this one out as well and see if we can get our cores surfaced so that we can take a look at them under the microscope. All right. So we have with us this extension cord. So would you see if we can maybe run it like this and go out the door? The sander is also messy. And so
ये बंद है फिक्स्ड है उधर से देखो
You can
I mean, that works, but yeah, it takes a lot of work.
Should I turn it on?
पूरा खाना खराब हो गया।
Okay. So, would somebody back in the room grab our samples that we mounted yesterday? All right, how are we going to do this?
फोन का
तुम बना रहे हो, मुझे दे दो।
वीडियो बना
ये इससे मिल जाएगा ना, ये बना रहे हो।
चाहिए फिर अपलोड हो
ये पीछे ओपन आगे से बना।
Okay. Nice. All right. So these are our Azadirachta indica, which we think might have tree rings. Ay. We should have mounted these outside. I think we couldn't see the fibers really well, but do you guys see the fibers? They're not straight up and down, right? They're at a pretty strong angle, which is not great.
This one I think.
Okay, so I've set the sander like this because now we have this wall behind it, so there's nobody standing behind it. However, if a sample were to really fly, it could bounce off this wall. So what I'm trying to do, if this is a rough sandpaper and a strong sander, if I push, it'll just go, it'll eat the whole piece of wood in a minute. That's not the goal. The goal is to have a flat surface close to halfway down the core. So if we think of the core as a cylinder, we want to be close to halfway, maybe a little bit less than halfway, because we still have more sanding to do after this. The most coarse belt, the grittiest belt, is going to remove most of the wood. But then the other sanding belts will also remove some, okay? So let's work with this first. So I'm going to lock this on so it'll stay on and keep running. I think that with the sort of rough surface that it's on and the fact that I'm not pushing on it at all, I think it's not going to move. But just in case, with the first run, we'll just have to pay attention to it. So there's a power switch on that thing there. So if anything doesn't look good, you can hit the power there too, okay? All right, so we... Is there a little table or something we get it closer to eye level, because it's a little hard to see what it's doing. But if you had a lot of pinus, for instance, then you need to get what's called a belt eraser, and it's like a pencil eraser, but it's huge. It's this big, and you hold the belt eraser, and it cleans the gunk off of the belt. It does a really good job. find the place where they kind of lock back in their original shape. But this is nice.
Could there be a possibility that there was a scar and
It's not fitting.
okay.
Yeah, they could have fit together. But yes, it could be due to a scar for sure. So we often encounter scars in the trees like that. So what I'm trying to do is make it pretty level. This belt is really quite rough, so if you were watching, it was kind of bouncing. It was hard to hold it at the right position. I don't want to press too hard because then it'll start to, it could eat this wood very fast. So I'm pretty content with this right now. I think that's pretty good.
Can I please touch it?
Yeah.
It's not so soft.
This is the roughest belt. Boy, this wood is going to be very interesting under the microscope. Look at that. This is the roughest belt, so yes, it's not very soft. When you complete the sanding, then it'll get quite a bit softer. So let's grab the other sanding belts with the other sander, and let's go ahead and finish this one. Yeah, let's finish this one, and then we'll do some others. Would one of you grab? There was a box that this was in. Did you get that box?
इसका छोटा डब्बा ले आओ जो है कुछ.
This one's going to be a little more of an experiment because I'm not sure. We don't usually use this kind of sander, so I'm going to have to play around with it. Yeah, we can use that. So that's another little type of dust. These are all dust collectors. And when you're working in a wood shop, outside it's not really a problem, but in the wood shop, you would want to... No, we don't need that. I'm not sure what that is. Let's see what our choices are. So we have 150, 100.
Start with 100 or 60.
So 60 is quite rough. Yeah, the 60 is
Almost.
maybe even rougher than what's on there.
It looks rougher than.
I'm going to go with the 150. So you can feel that. And if you feel the difference, this is more smooth. So these kinds of...
What is this? 150 is
150.
Unit? What unit is it?
It's a unit related to the grit. So the higher the number, the finer it is. Yeah, exactly.
CWW.
So in a store that sells goods for working in with what we call hardware, I don't know if people use the same term here, hardware store. So one can buy sheets of sandpaper, usually up to about 220. And that's about as fine as people use for things like making furniture or in a construction. So they don't sell the very fine sandpaper. But I've brought some other sandpaper that we can use as well. Which actually, would you mind, where I was sitting, there's little papers that are inside of a little plastic bag. Alright. So the way this works is it curves. So you set it on the sander and you bend it, and then it curves under these things. It locks, yeah. So there's that. And then this one, you have to open it up. It goes like that.
Slide it. Yes. This side also.
Okay, we'll come back to that in a second. Let me try to...
Otherwise,
Can you close that one? Yeah, there you go. Goes down and in.
No, I
Yeah.
think in this direction.
Yeah, and then we'll open that one back up. Okay.
अभी तो फिर अडेप्ट हो जाएगा लोकली अडेप्ट तो होना ही पड़ेगा
एक जगह कहीं आपने ज़्यादा ज़्यादा घिस गया और इधर कम
So this is a vibrating random direction sander. You don't see it? Let me go, I'll be right back. Yeah, there you go. Okay. So this one has to be a little bit more experimental, I'm sorry. But let's try it like this. It's a weird switch. Okay. You ever feel it now? It's smoother. Yeah. So now this time we're not really trying to press hard and take more wood off. We're just polishing. We just keep polishing and cleaning. So now we go to some specialty sandpapers, and these are papers that you cannot buy just in the regular store. You have to order these papers because these are very fine grit. So this is 40 micron, 30 micron. So it's the surface that's not printed on is because you can almost not tell anymore which side is intended to be used. And then I might have, yeah, these are 15, or this large one is a 15 micron. This is the finest that we use. It's almost like brushing it with a cloth instead of, sandpaper, right?
How long it lasts?
What depends on how long it lasts is mostly what you're asking it to do. So if you come to the wood and you push hard and you're trying to remove wood, it doesn't last very long. It's not intended to be used that way. It's just, it's polishing it. So we start with the 40, we go to the 30, we go to the 15, and at that point we're just buffing it. We're polishing it more than sanding it.
Approximately 8-10 samples.
So let's set that on the ground. All right. May I have the sample back? So. I don't think we have any scissors with us today, so what we would normally do is cut this into some smaller pieces, but I'm just going to use the edge. So that's 30, this is 40. So 40 is the roughest of these papers. So we started with this, which I don't remember what this is, but this is about 100 or so, it feels like. Then we went to 150 with the little sander. Now we're going to 40 microns. So the numbering system changes, and now the smaller the number, the finer the paper. It's just the way it is. And so we take this and just lightly, I'm trying to do it lightly, but I'm also trying to cover the whole surface of the sample so that I can get a good coverage and not leave. What happens is when you watch with your normal vision, it seems perfect, it seems smooth. But then when you look under the microscope, then you see all these striations and lines that the sanding has left behind. So every time it has smaller grooves, smaller grooves, smaller grooves, until at the end it's just a polish. It does feel nice and soft. Now we go to the 30. Especially with the 15, it's hard to tell which side is the sanding side because it's so soft.
फाइनली हो जाएगा तो काफी ड्यूरेशन 4 को 10,000 हो जाएगा तो डेंड्रो वाला कारपेंटर आएगा डेंड्रो कारपेंट्री हाँ?
Feel it now. Another thing that I'm trying to do is I'm trying not to round off the edge. I'm trying to keep the paper flat, because if I round it off, then when I look under the microscope, I can't focus on, I can only focus on one place at a time. So if it's rounded, I'm losing information. I can't see as much. All right, so now we'll use this 15 paper. And here we're just gently.
हम लोग वाला सैंपल ये है क्या?
वहीं रखा है।
कल लेके
Feel it now?
मैंने रॉक्सवेरिया के हैं मेरे 15-20 सैंपल
हम लोग के 20 के
all done.
It's like, it's a more
Even the
silky.
rings are even like visible better than previous.
Sometimes there can be dust. So we might almost like use the see. That's why I changed. All right. So let's look at this under the scope.
Yeah.
But what I am completely amazed about is if these things are all rings, this is a very old tree. I wonder if that's possible.
It has CBH diameter of 50.
50 था? ficus. आप थे हमारे साथ?
हमारा था 34 था सर।
34 हाँ।
151 CPs.
बहुत stressful size है।
And I've not done a good enough job of sanding it yet. I can see that there's still a lot of striations. Also, it looks like that second piece after the break we mounted sideways, which is too bad. But the first piece we can see pretty well. It's just that it is still needs more sanding.
But it's clear.
It's getting there, yeah. We still have to work on it.
Yeah, polishing is needed, but it's clear.
And if you can see the difference between the part where you can clearly see the cells and the part where there's still some marks from the sanding, that lets us see what we have yet to do.
And those spots between rings, resin, or no, maybe
Vessels?
latex vessel,
Vessels, yeah.
Vessels carrying latex and all that.
Oh, well, I don't know about latex.
And latex
But-
means ficus,
but,
they have that.
Uh-huh.
But it's very clear.
This is the first ficus wood I've ever looked at in my life. so-
Very clear.
Yeah?
I can't interpret, yeah.
Satish, I wonder if in the office here they would have some scissors that we could borrow?
Yeah, I have, yes.
Um,
Right now, tomorrow.
Well, I wonder if in the office downstairs, the director here, or there's an office by the front.
If they have here, or what I'll do, right now we want?
Well, I don't want to make you go anywhere.
I'll
I
just,
wonder if we could ask these people if we could use their scissors for a second. Because those big sheets of sandpaper, it's better to cut them up. It's hard to sand with that.
You need right now, huh?
I have a
Knife, Swiss
Well,
knife.
we can try that, sure. Yeah, we can do that.
right seat for this one, right side is the left side of the right side of
That'll work.
No, that Caesar.
Put the knife forward.
Yeah.
एक बार नीचे ऑफिस में जाके पता करो
एक्चुअली ठीक से माउंट भी नहीं हुआ होगा, इस वजह से ऐसा हो सकता है।
फिक्स कर लो, उनके बाद शायद चेंज हो गया।
फिर नहीं फिक्स कर लो।
Okay, you guys are taking turns looking at the ficus, that's good. So while that's going on,
सेट करना उसका अभी और कलर ब्लैक की साइड में इसे खाली सेट करना पड़ेगा। उन्होंने हिला दिया था।
पहले मैं सोच रहा था इतना क्लियर होगा जितना ये वाला है कॉन्फर्स वाले अब नहीं देना है।
नहीं वो ठीक है ये देखिए इसको
आपका नंबर है क्या? थोड़ा सा है।
वो अपने अकॉर्डिंग एडजस्ट कर लो। हाँ आप अपने अकॉर्डिंग कर
हाँ
सकते
ठीक है।
या फिर चश्मा लगा के देख सकते हैं।
मेरे पास नहीं है।
अच्छा
बट नंबर
सॉरी।
It's easy to go too far, so that's why I kept stopping to check, because what I'm aiming for, we can leave it plugged in for a minute, I'll do the other one on this sample. What I'm aiming for is to be just above halfway, and I also want it to be flat the whole way and not kind of go down and up and things like that. So that's why I keep stopping and checking instead of trying to be fast. If I try to do it fast, then maybe I destroy the core. And again, for us, that's not a big problem, but if it's your real study and you climbed the Himalaya to get this core, then you don't want to ruin it. Okay, we'll do the other one on here, and then we'll jump to this. Okay, so I'm content with both of those. I'm really curious to see what this wood is going to look like. This is Ziziphus. Wow. Interesting. Okay. Another thing that I want to do is to have the surface be very flat on top, and I didn't quite do that with this first one. Actually, could you plug it back in for a minute? Can you plug the other one in also? Thank you. Because I need to fix one thing on this. I want it to be flat on top again because under the scope, you focus on an area, and if it's not flat, then you lose the focus. Now it looks good. It's hard to hurt yourself with this, I think. The on-off switch is like this and like this. It's a little bit difficult to find. And this one we can use. I'm not really pressing. I'm simply holding it next to it and letting it polish. I'm not trying to cut wood out of it. Okay, so I'll hold it. Would somebody like to sand the second core? You want to do it? Okay, so hold your fingers. Don't hold it like anywhere close to it. Hold them back. This is the core we're going to sand, so hold it in the about like that. Okay? Okay, take it off and look at it. So how does it look? Does it look like is there anything that we need to do on either of them? So we don't want to sand it too much. You know, we just want to have a nice, consistent surface. We want it to be flat. We want it to be wide enough. This is on the very first machine. Wide enough to be as much as we can see out of this core. If you go too far, then it starts to get into the bottom part of the cylinder, and all of a sudden it starts to shrink, which is no good. I think it's good. So what I would propose that we do is move through several cores. There's a second extension cord that's in a bag, a white bag sitting on the chair where the gear was. Because this you can only plug in one thing at a time, right? Why does it have so many plugs?
But we don't know. First try that.
And then what I would propose is if you would take this one and work with the students and let them do multiple samples, and I will work with this one, and
that is more dangerous.
We'll do some more. Excuse me?
That is more dangerous. So
it is, yeah.
Better you handle that.
So when we sample this, we want to use the red paper first.
Sir?
Excuse me.
Yes, okay.
No, you're totally right. We
want
to use this first. Push it at all, it just disappears. I think this is about as good as it's going to get. It's too low. But I mean, I'm not sure if we're going to be able to see. In some places it looks like distinct rings, but in other places not. Yeah. Okay, so this can move on to the second. Yeah, this one looks good. This is probably the acacia. I mean, it does look like you can see something like wind. I don't know. You have to sit in, not at an angle. Okay. Would somebody like to try this machine? A lot of people want to try this machine. Okay, why don't you come over to this side. All right. So when you do the second one, it's more bouncy over here. It starts to bounce the wood. It's better on this area here. Also, you don't want to accidentally mess up the one that's already done. So you're going to hold it, fingers well above the wood. Try not to tip it one way or the other. Try not to let go. But if something bad happens, just back away from the... If the piece goes flying, there's nothing... Once it's gone, it's gone. You can't try to grab it or anything. So just move your hands away, okay? Yeah, good idea. Yeah, you want to pull your sleeves up a little bit? Okay. All right. So it's the middle core that we're going to try to do. Okay? Farther up. So not like this, but like here. Okay. So here, this part's pretty good, and that part needs a little bit more to come down. And you see the thickness? Yes, yes. Yeah, okay. More, a little bit more. Try to hold it really vertical. I don't think mine is as vertical as it should. A little bit more. That looks very nice. Yeah. Exactly. Okay. Good job. Somebody else?
I will also do
one. You do the next one.
Yeah.
Okay. Ready? Yeah.
घड़ी निकाल दो आप लोग करिए हाँ घड़ी उतारिए भाई हाँ वो ring उतार लो भाई ring
What happened to my watch?
no nothing will happen यार चलो कितना भी मत करो
Okay. Yeah. So fingers higher up.
yeah
Near the top of the wood. Okay. All right. Good? So in this case, it went down a lot right there. Don't try to take that down anymore, but try to take that little end bit out. So just a little bit that way. Okay? So could we take this to the next sander?
Just to
Yeah. Want to go?
कोई और है? This one?
Sure, big one. Okay. So yeah, that's a dangerous spot. So we definitely want to go the other direction because the belt is going like this, and we don't want to have the belt grab that piece and pull it off. We want it to go this way. And yeah, fingers roll up. Okay, so what do you think? Yeah? Yeah. This was very low. So try not to go that low. And basically this is a long sample, so it's better to ficus also. This is the good ficus, the one that doesn't rot or doesn't melt. All right. Thank you. So this is a little bit low.
Yeah.
It's all the way down to the wood.
Yeah.
That's the lowest that we would want to go. Ready? So it's good not to stand up there just in case. Pretty consistent. It could go down. A little bit high in the middle, yeah. Okay. So if you can just clean that up, then we should be good. It's pretty good. It's fine. So, and it takes practice. Everybody's doing it for the first time. So what you did that was very good was you went slow, you look, you go slow, you look. It's better to go too slow than too fast, because too fast, then it's all over. Also, the hardness, that ficus wood is so soft it just disappears.
Yeah.
This is a lot harder. Give that to me. So, it's already one.
टेढ़ा कर दिया
आपको ये मिला अच्छा हो गया
मैंने वो पूछ किया है 3 वाला नहीं है
So, yeah. Also, it's a little bit tipped because when you're holding it on there, you're leaning a little bit that way. So try to make it very vertical. And then come back to here and do it like that. And then pull forward and it's going well. This is going good. Okay, you ready? Take it off until it's good. Yeah, I think that looks good. All right, you want to do the other one? Or does somebody else want to do it? Yeah, there we go.
Yeah. Okay.
Fingers up high. Okay.
अभी नीचे fingers
those
नीचे
fingers too.
और
All right, ready?
सिर्फ इधर वाला अनुराधा इधर वाला होगा
It's good in terms of the depth, but if you look at it, it's a little bit of an angle on top, and that comes from bending it a little. So try to just a little bit more, very vertical. Okay. That's good. It just takes a little tiny bit. Okay, I think we should stop so that we can eat. We can